In today's video, we are going to be talking about the heat diffusion equation, which goes as follows. It is the derivative of the temperature with respect to time equal to our thermal diffusivity alpha multiplied by the second derivative of temperature with respect to position. As stated in our earlier video, we know that our thermal diffusivity is equal to thermal conductivity divided by our density times our heat capacity. Well, where does this equation even come from? How do we derive this? Well, this comes about through an energy balance. So let's take an example of an energy balance. Let's say that we have this rectangular prism. Over here on the left, we're going to say that this position is at x is equal to 0. And over on the right side, this is going to be at a position of x is equal to L. Now let's split this rectangle into sections. For the sake of this example, we are going to say that we are concerned with the heat flow through this center brick. Let's first state some initial and boundary conditions. To do so, we're going to have to write our temperature as a function of both position and time. Just as you can see here, it is both a function of position and time. So for this example, we are going to say that the temperature at position x is equal to 0 at any time t is equal to 50 degrees Celsius, while the temperature at position x is equal to L at any time t is equal to 80 degrees Celsius. And for our initial condition, we are going to say that the temperature at any position x at time is equal to 0 is 20 degrees Celsius. As I said before, if we are concerned about the heat flow through that center brick, we know we're going to have some heat entering on the left and some heat leaving on the right. We'll denote this as Q left and Q right. And each of these sections have some change in position delta x. The net heat flow can be described as the heat entering minus the heat leaving. We already said that the heat entering is Q left and the heat leaving is Q right. Now, if we want to talk about the energy of this brick as a function of temperature, we'll have our temperature. And how do we relate temperature to energy? Well, we're going to multiply that by the heat capacity. Temperature has units of Kelvin, and heat capacity has units of joules per kilogram Kelvin. Multiplying these gets us 2 units of joules per kilogram. Now we want to relate kilograms to spatial units, so we can start talking about joules per cubic meter or energy per volume. To do that, we're going to multiply by density. Density has units of kilogram per meter cubed. Now we are finally in units of energy per volume. Going back over here, we can expand our Q left and Q right terms. Q left can be represented using Fourier's law, which we know is negative the thermal conductivity multiplied by the area multiplied by the change in temperature with respect to position, and over here evaluated at x from the left. Q right, similarly, can be written out as negative the thermal conductivity multiplied by the area multiplied by the change in temperature with respect to position, evaluated at x from the right. And just for clarification, when I talk about left and right here, I'm not necessarily talking about this left and this right, but rather the left side of this brick and the right side of this brick. So this equation over here is currently in units of energy per volume, joules per meter cubed. If we want this in just energy, just joules, we know we need to multiply by the volume, because volume has units of meters cubed, and that gets us to units of just joules. Taking the derivative of this with respect to time, we'll find that the derivative of the volume multiplied by the density, the heat capacity, and the temperature with respect to time now becomes our net heat flow. Or like we said over here, Q net. And we know that Q net is equal to Q left minus Q right. So let's write that down. We have the derivative of volume, density, heat capacity, and temperature with respect to time equal to the negative thermal conductivity multiplied by the area multiplied by the change in temperature with respect to position evaluated at x from the left minus a negative right here, so plus the thermal conductivity multiplied by the area multiplied by the change in temperature with respect to position evaluated at x from the right. Now, as we can see here, this volume term is kind of an outlier. We don't have volume in the rest of this equation. So we can turn our volume into variables we already have. We're going to say that our volume is our change in position, delta x, multiplied by area. Delta x is in units of meters, and area is in units of meters squared. Multiplying those, we get meters cubed, which is good. That's the units of volume. Substituting this in, we'll get the derivative of delta x, A, our density rho, our heat capacity, and our temperature with respect to time is equal to our negative thermal conductivity multiplied by our area multiplied by our change in temperature with respect to position evaluated at x from the left plus our thermal conductivity multiplied by area multiplied by our change in temperature with respect to position evaluated at x from the right. We can simplify this doing a few things. We can take out our delta x, A, rho, and C variables out of our derivative because those are fixed values and do not change with time. We can also take out our Ka from the right. So let's do that. We'll have delta x times our area times our density and heat capacity multiplied by the change in temperature with respect to time equal to our thermal conductivity multiplied by area multiplied by the change in temperature with respect to position evaluated at x from the right minus our change in temperature with respect to position evaluated at x from the left. Looking at this, we can see our area cancels on both sides. We can also divide our thermal conductivity by our density and our heat capacity. We are then left with delta x times the change in temperature with respect to time is equal to our thermal conductivity divided by density and heat capacity multiplied by our change in temperature with respect to position evaluated at x from the right minus our change in temperature with respect to position evaluated at x from the left. Dividing both sides by delta x we are now left with the derivative of temperature with respect to time is equal to the thermal conductivity divided by our density times our heat capacity, which we said earlier is our alpha, our thermal diffusivity term, multiplied by the first derivative of temperature with respect to position divided by a change in position. That comes out to be the second derivative of temperature with respect to position. And look at that. That is our heat diffusion equation. Okay, so now I want to take our same heat diffusion equation, and this time I want to represent this using finite differences. So I'm going to draw an example of a long rectangular rod, and this rod is going to be split into several, hopefully even, sections. And each section has some change in position that we'll note as delta x. Now, to keep track at whatever section we're at, we're going to use a counter, and we're going to use the variable I. So over on the left, this is going to be at I is equal to 0. And on the right, this is going to be I is equal to 100. We're just going to imagine that we have 100 slices here. Now, to represent our position, we're going to have to multiply our change in position by our counter, whatever slice we're at. And to model our time, we're going to have to take our change in time and also multiply by a counter, and we are going to use the variable n as our counter for time. And we're going to say that delta x is equal to 0.1 meters, while delta t is equal to 0.1 seconds. Now, using this model, we can have an equation that looks like the temperature at the position to the right of you at some time n minus the temperature at your position at some time n divided by the change in time. And this equation is analogous to the left side of our heat diffusion equation, the change in temperature with respect to time. Now, in order to get the right side of our equation, the second derivative, I'm going to draw out another bar, but this time I'm only going to divide these in 3 sections. And the middle section is going to represent the temperature at your position at some time n. And to the right of it, it's going to be the temperature at your position plus 1 at some time n. And to the left of it, this is going to be the temperature at your position minus 1 at some time n. Now, we know from before we had this net heat flow equation that was the heat coming in from the left minus the heat leaving on the right. So for Q left, we can take the difference in these two temperatures and divide by this change in position, delta x. And for the right side, we can take the difference between these two temperatures and divide that by this change in position, delta x. And then we're going to have an overall delta x representing the entire length of this bar. So writing out Q left, it's going to be the temperature at the position to the left of you at some time n minus your position at some time n divided by delta x. And we are going to subtract Q right, which is going to be the temperature at your position at some time n minus the temperature to the right of you at some time n divided by delta x. And this is going to be divided by our overall change in position, delta x. And this is equal to the left side of our equation multiplied by alpha. So let's break that out. We're going to have the temperature at the position to the right of you at some time n minus the temperature at your position at some time n divided by a change in time, which is equal to alpha, or thermal diffusivity, multiplied by the temperature at the position to the left of you at some time n minus the temperature at your position at some time n minus the temperature at your position at some time n plus the temperature to the right of you at some time n. And this is divided by position, which gives us delta x squared. And this represents the second derivative of temperature with respect to position. So now we can combine these like terms. So this becomes the temperature at the position to the right of you minus the temperature at your position divided by a change in time is equal to our thermal diffusivity multiplied by the temperature to the left of you minus the temperature minus 2 times the temperature at your position minus the temperature plus the temperature to the right of you divided by delta x squared. So we are going to be concerned with solving for this value. So we are going to have the temperature to the right of you at some time n is equal to, moving these other values to the right, the temperature at your position plus the thermal diffusivity multiplied by the temperature to the left of you minus 2 times the temperature at your position plus the temperature to the right of you, all over the change in position squared multiplied by a change in time. We're going to rearrange this because we are going to be modeling this in Excel in a few minutes. So just to make it easier, we're going to make this the temperature at the position to the right of you equal to the temperature at your position plus the thermal diffusivity times the change in time all over the change in position squared times the temperature to the left of you minus 2 times the temperature at your position plus the temperature to the right of you. Now we are going to model this in Excel. Okay, so now I want to model the equation we found for heat diffusion using finite differencing in Excel. So I'm going to make this variable r dot as our thermal diffusivity and give this a value of 0.1. If we remember back to our original example, we had that rod and at time was equal to 0. Our initial temperature was 20 degrees Celsius. And then after time was equal to 0, the temperature on the left side of the rod shot up to 50 degrees Celsius, and the temperature on the right side of the rod shot up to 80 degrees Celsius. And then we can say that this column is representative of our times. We started off at time is equal to 0, and after that, each time increased by 1. So this cell is going to be equal to the time before it plus 1. And we can drag this down for 600-ish
cells. So we'll have 600 different times. And we're going to make these formulas, so we can highlight this, go to formulas and do create from selection. And yes, all of our variables are on the left side, so that's good. And then if we remember that at time is equal to 0, this was equal to our initial temperature. And we can drag this initial temperature over for like 15-ish cells, whatever that is. And then we remember that we can put this value as the temperature at the left side of the bar, and this as the value for the temperature at the right side of the bar. And these are constant no matter what time we're at, so we can drag this all the way down to 600. And we can do the same for the right side of the bar. That temperature is not changing, so we can drag this down as well. It'll be the same no matter the time. Okay, and then now we can represent the temperature at this cell using our equation that we found. So we can say that this is equal to our initial temperature plus the thermal diffusivity. And if you remember, the thermal diffusivity was multiplied by a change in time, delta T, divided by a change in position, delta X squared. And I'm pretty sure in the first video I made those 0.1 meters and 0.1 seconds. But just to make this easier so that we don't really have to plug in any crazy numbers, we're just going to say those are 1 meter and 1 second. And this was multiplied by the temperature to the left minus 2 times the temperature, 2 times the initial temperature, plus the temperature to the right, which is just going to be H2. And we'll hit enter. And yes, that's okay. So now we can see that we got a temperature of 23 degrees. And this formula is going to stay consistent throughout all of these. So you're going to drag this over. And then we can also drag this all the way down for those 600 values because that equation remains the same. Okay, now scrolling up, we can see this point where the middle of our rod finally starts to change temperature. So those temperatures start slowly creeping in, and finally the middle of our rod is experiencing a change in temperature. Now we use this value of 0.1 for our alpha, our thermal diffusivity, but you'll note that if you change this to be equal or greater than 0.5, we actually reach a critical value where Excel can no longer correctly calculate due to rounding errors. You'll start getting negatives. It just won't be able to accurately describe the equation that we derived. And so that is how you model our equation for finite differencing within Excel.